Today we're going to go over 3 more convergence tests for when the first ones we learned last class don't work. If they don't give us enough information, sometimes we have to go a little bit farther. These 3 are significantly more weird than the first ones, but they also come up a lot less. First off, this one's not so bad. The integral test. This is nice because it connects to what we learned a couple of units ago. If the definite integral of a function converges, then the infinite series of that expression, that function's expression, also converges. If the integral diverges, so does the series. So we can connect this to what we learned last unit. We'll try and find the definite integral from 0 to infinity of, you can stick with the n over n squared plus 7, or you can replace it with an x if you're more comfortable with that. It doesn't matter. If the definite integral from 0 to infinity of n over n squared plus 7 in respect to n diverges, then so will the series. And if this integral converges, so will the series. And so we have to remember back how we handle these definite integrals to infinity, which we learned earlier in the year were called improper integrals. We turn it into a limit. So we take the limit as b approaches infinity of the definite integral from 0 to b of n over n squared plus 7 dn. And hopefully you recognize that. You probably can't recognize that when the n doesn't look anything like an n. But hopefully you recognize that one, and your first thought should be, oh, I'm trying to take an integral here. Look, there's an n squared in the denominator, and its derivative is right there. Well, that is awfully convenient. So I will use u substitution here. If my u is n squared plus 7, then my du is 2n. Remember, this is a definite integral, so I'm going to want to change the limits of integration also. Well, if I plug a 0 into n squared plus 7, I get a is equal to 7. And b, if I plug, well, just b squared plus 7. This might make it more complicated than it needs to be, but that's okay. So we're going to have to put in our 1/2 and 2 there. We need this to be a 2n, so I'm going to stick that in there. So this definite integral is equal to, remember, it's still a limit. The limit of the definite integral from b to infinity of 1/2 the integral of from 7 to b squared plus 7. I know that looks weird, but remember, we're going to make that infinity in a minute anyway, or take the limit as that approaches infinity, so we don't have to worry about that. And so now it's just the 2n dn cancels out and becomes du, so we've got du over u. So this is just 1/2 the ln of the absolute value of u, evaluated, oh shoot, I forgot my limit. The limit as b approaches infinity of 1/1/2 the ln of the absolute value of u, evaluated from 7 to b squared plus 7. And if we try to plug in that, we still have to do the, we're finishing up the definite integral inside the limit. Still the limit as b approaches infinity, but that would be the ln of the absolute value of b squared plus 7 over 2 minus the ln of 7 over 2. But here's the problem. This is an infinite limit. So this integral converges. No, diverges. Because, like I said, if we try and take the infinite limit here, that will keep growing forever. So the series diverges too. The reason to do this is because the n over n squared plus 7 doesn't really fit into any of our previous examples. It's not a p-series, because a p-squares couldn't have that n in the numerator. It passes the nth term test, because those terms will get smaller and smaller and smaller. It's not alternating, we can't use that. It's not a harmonic series, we can't think about that. So none of our other series worked. So the integral series was helpful here. We can conclude that the series diverges. By the way, the ratio test also every once in a while comes up when you're doing convergence testing, having nothing to do with intervals of convergence, but very rarely. I can't remember ever really seeing it outside of the interval of convergence, but your textbook does include it on the list. So I will just remind you that the idea of the ratio test is if you can't take the common ratio, if every ratio of one term divided by the term before it isn't always the same number, so it's not a geometric series, well, you can at least take the limit of that ratio, and if that limit of that ratio is less than 1, then the series must converge. Remember, all of this is happening because we're talking about places where that limit is equal to 1, usually. And so the ratio test, usually by now we've already kind of seen that it doesn't help. So we're not going to turn to it very often. The next two are, well, let's just try. The first one is actually also, again, not too bad. This is called the direct comparison test. This is for when one of your other tests, like your p-series test or your harmonic series test or something like that, when it should work, it just doesn't quite work. That's what the direct comparison test is for. Here's an example. Well, I'm going to read that green writing in just a second. I'm just going to look at this series first to kind of clear up why we need this. 1 over n squared plus 7. Well, that sure looks like a p-series with a p of 2. So it sure looks like it would converge, because we know that's what the p-series test tells us. If the p-series has a p that's greater than 2, that exponent in the denominator is bigger than 2, it'll converge. The problem is that this isn't exactly a p-series. So I can't say that it is. You got to be careful not to say something is in a class that it doesn't exactly fit into. Luckily, we don't have to worry about that so much. We can use what's called the direct comparison test and compare this to a p-series. As long as the expression in the series that you're looking at is always below, always smaller than the terms of a p-series, and the phrase we use here is if the tail of the series is bounded above, that means it's always below. I know it sounds backwards that the words bounded above means is always below, but it basically means there's like a ceiling on top of it. And if that ceiling is a series that we know converges, well, a bunch of terms that are always smaller than a series that converges will also converge. So look at an example here. Here is, if we look at the green ones for a second first. I just lost power in the building. So this video is still working, but my monitor is shut off. Interesting. We'll be right back after these brief messages.